Okay, so here we are for a second video on sequences, and I watched back a bit of the first video, and one of the things I learned really quick was with this camera pointing down at the table, the microphone doesn't work very well. So I'm going to see if I can't get a better microphone situation organized before I make a bunch more videos. I should be able to get that squared away for the next one. So my apologies on the weak audio. I didn't know that was going to be the case. We just have a couple topics about sequences we want to cover, starting with bounded sequences. We want to talk about recursive definitions, and then that'll wrap up our 8.1, and I'll get some material up on 8.2 tomorrow. That'd be Wednesday. Okay, so when we're talking about sequences, we sometimes talk about a sequence being bounded. And so if we had a sequence that was something like 2 plus 1 over n, okay, we could write out a few terms there. And what we would want to do is look and see if there was a boundary on the values, and a place where the values never went above or below. And so let's take a look at what happens. When n is 1, then we have 2 plus 1 over 1. So 2 plus 1 over 1, of course, is 3. Now, when n is 2, we get 2 plus 1 half. 2 and a half, I think I'll write that as 5 halves. And then when n is 3, we get 2 plus 1 third. 2 plus 1 third. 2 is 6 thirds and 1 third, 7 thirds. You know, it's starting to look like there might be a pattern here. What happens on the fourth term? 2 plus 1 fourth, so that would be 8 fourths plus 1 more, 9 fourths. I see the pattern now. I'm sure you guys can all write the rest of the terms pretty quickly and easily. So what we want to do now is we want to see, is this sequence bounded from above? And when we look at this number 3 and we consider all these values further on, we see that we're always adding on to 2 a value 1 over n that's getting smaller and smaller. So the first term is the largest term we're ever going to see. So we could say that a sub n is bounded above by 3. It never goes above that value 3. So 3 is the boundary for the values in the sequence. Now, what would be the value bounding it below if there is one? So in this case, to find it, we see that we're adding smaller and smaller bits onto 2 as we go along, but we're always going to be adding something onto 2, because no matter how big n gets, when we stop to look at it way out there near infinity somewhere, it's got a little tiny bit of value to it. So it would be just a little tiny bit higher than 2. So we would be able to recognize that a sub n is bounded, below by 2. Now, if you have a sequence that doesn't have a boundary, so let's take an example of that. Let's suppose that we had a sub n was given by 2n plus 1. And let's write out a few of those terms. So when n is 1, we get 2 times 1, 2 plus 1, 3. When n is 2, we get 2 times 2, 4 plus 1, 5. When n is 3, 2 times 3, 6 plus 1, 7. And you can see the pattern here already, can't you? 4 plus 1, 8 plus 1, 9, and so on. So this sequence would be bounded below by 3, but it would be unbounded above. So we would say that a sub n is unbounded above. So there's occasionally applications of sequences and series, which we'll be working on in 8.2, where simply knowing what the boundaries are is enough information to move forward with your project. So engineering is often about not letting loads go beyond a certain level or determining the maximum capacity of something. And so if you know that your boundary of your function doesn't allow you to overload your structure, then that's enough information to know. You don't have to know what the boundary is or what the limit is necessarily, as long as you know that you're not violating your safety factor. So sometimes just knowing that it's bounded and by what number is all you really need. Okay? Now the other little topic we want to talk about is something called a recursive definition. So we could have a sequence that has a recursive definition. And so we sometimes use the word recursion to talk about the process of generating the terms. And the idea behind recursive is that each term in the future relies on one or more of the terms that preceded it in the sequence. So an example of that would be the sequence which is called the Fibonacci numbers. Most people have seen this before, where the first term is 0 by definition, the second term is 1 by definition, and then each successive term is found by adding the 2 before it. So we would add 1 plus 0 to get 1. The next term would be 1 plus 1, 2. The next term would be 2 plus 1, 3. The next term, 2 plus 3, 5, and so on. So Fibonacci was an Italian monk, and the story goes, and I don't know that this is necessarily factually correct, but the common story is he was studying the reproductive rates of rabbits at the time, and he noticed that future generations, the number of rabbits in a future generation followed this pattern. Presumably, he found the pattern over here somewhere with many rabbits and worked his way back to see where the starting point might have been. So that's the Fibonacci sequence. Okay. So the idea here is that we have recursion. We use the previous terms to find the next one. So we would write something like this. We find the nth term by taking the n minus 1 term and adding it to the n minus 2 term. So we find the next term in the sequence, say 3. So we find the 1, 2, 3, 4, 5th term in the sequence, okay, by looking at A4 and adding it to A sub 3. And that would be the 2 and the 1, respectively. So in general, this is a recursive type of definition. You find the next term by using the previous terms. Okay, so we could have another recursive definition, and it could look like this. And so if we do this, let's make a few of the terms and let's see how it works. Oops, I need to go to a previous n minus 1. Okay, so when n is 1, we're going to have to give a definition point, a starting point. So let's say that when n equals 1, our value is 1. Now we should be able to use our recursive formula to generate all the following terms. So when n is equal to 2, we have 2 times a sub 2 minus 1. So the term before it, that's 1. So 2 times 1, 2 minus 3, negative 1. Alright, so now the next term, where n is 2, and we're looking for a 2 minus 1. I'm sorry, this is n equals 1. This is n equals 2. We're working on 3. So when we're looking for a sub 3, we need a 3 minus 1, a 2 right here. So it's going to be 2 times negative 1, that's negative 2, minus 3, negative 5. And so now to get our fourth term, we would go back and use the third value. So this would be 2 times negative 5, negative 10, minus 3, negative 13. Anybody see a pattern yet? After this first step, what's the pattern that we see? We go negative 4, negative 8. I wonder if the next one will be negative 16, or maybe it'll be negative 12. I bet it'll be one of those two. It'll go down by 12 or it'll go down by 16. Okay. So this is how you would find your terms by recursion. Finding the limit of this type of sequence can be quite challenging. So, all right, that finishes up our section. I had squeezed a lot of it into that first video. I did want to point out to you that there's a table of common limits for sequences that are common sequences, and that's on page 484. So that might be helpful in trying out some of the homework problems that go along with these two videos in the section 8.1. So I'm going to see if I can't get a better microphone situation organized, and then tomorrow morning I'll go to work on the 8.2. We'll get some more videos up, and then I'll try to get ahead of the game a little bit here so that you don't have to wait for me to see the next wonderful math video. Thanks for watching.